This lesson is all about the conic sections. Now that we have studied the different types of conic sections, we turn to find out how these curves are all related to one another. The name conic section derives from the fact that you can produce a circle, parabola, ellipse, and hyperbola by intersecting a plane and two cones that are oriented vertically so that their endpoints are touching. Let's take a look at that and see what that looks like. So here I have two cones that are oriented so that their points are touching one another. And I have a plane in the center of this setup that's vertical, or I'm sorry, that's horizontal right now, just lying in the XY. But I can move that plane. And what I'm going to do is I'm going to translate it up just a little bit. And then let's tilt and look inside the upper cone at the intersection of those two curves. So if I look at the intersection between the plane and the upper cone, this is the shape that we get. And this shape right here is clearly a circle. So just moving the plane up and down, I can get circles of basically any radius, assuming that this cone, the top and bottom cone, would go to infinity in both directions. So if I move the plane up just a little bit further, you can see that the circle still exists. It just gets a little bit larger in diameter. If I brought the plane down and looked into the cone that's lower, the same thing happens. So I end up with the circle at the intersection, and I can get that of any radius. Now, the next thing I can do is tilt the plane. So let me move it up a little bit, but tilt it just a little bit. So it's tilted slightly. Now if I look at the intersection between the cone and the plane, now that intersection is an ellipse. And depending on how I go about changing the angle of the intersection, I can get all kinds of different ellipses. So if I bring z down, then the ellipse gets smaller. If I change the angle of theta, the ellipse can get so that the major axis would be larger, for instance. And a lot of different effective changes I can make to that ellipse just by changing the position of the plane that's intersecting with the cones. All right, now let me do this. Let me continue changing the angle measure and change it to 45 degrees. And this only happens at 45 degrees because that matches the angle of the side edge of this particular cone, which happens to be 45 degrees. But I think it's pretty easy to see the intersection now is a parabola. So now we've gotten three of the different of the four different conic sections based on changes to the positioning of this plane. If I continue to rotate it, then what's going to happen is the bottom cone comes into play here, and we start getting hyperbolas. So if you'll see here, let me translate it a little bit more so you can try and see it a bit better. I think that's best I can do. But you can see, the lower half of this hyperbola is down this way, where the cone and the plane are intersecting. The upper half of the hyperbola is like right through here, where they are intersecting. And so by intersecting a plane and a cone, you can get all four of our conic sections. And I might be able to change the position of this so you can see the hyperbola a little bit better, but I think that might be the best I can do to see it. Let me rotate this way. Yeah, you can see it a little bit better in that angle. So you can see for sure, like here's the upper half of the hyperbola, and here's the lower half of that hyperbola. So in the intersection there. Another relationship that conic sections share is that if you algebraically expand their equations, they can all be expressed in the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. This is called the general form equation of a conic section. Usually the bxy term is not present because that term rotates the conic in the plane and is usually only included in more advanced studies of conics. So sometimes you'll just see that omitted altogether, but I put it here for completeness. Now the general form is not as easy to use when it comes to graphing conic sections, and so when presented a conic in general form, we often choose to express it in standard form first, before we go to graphing. And this is accomplished by using the process of completing the square. First, it is important to be able to identify the type of conic we need to graph. We can determine this by observing the values of a and c, which are the coefficients of the squared terms. So back to the equation here. This is the a and this is the c that I'm referring to. So if you observe those values, and you notice that a is equal to c, most likely you're dealing with a circle. And it's only very strange circumstances that you wouldn't be dealing with a circle. So you can rest assured you're probably dealing with a circle. If a does not equal c, very likely you are working with an ellipse. Okay, and this is provided that they are both the same sign. So you wouldn't have like a positive a and a negative c. That's a different situation, but let's just say they're both positive hypothetically. If one of a or c happens to be 0, but not both, because if both were 0, you'd end up with a line. But if one of those two is 0, you are most likely going to have a parabola. And if one of those happens to be negative, but not both, if both of them are negative, then you're back into, it could be a circle or an ellipse. If one of the two is negative, that's the important thing. So sometimes textbooks will say if a times c is less than 0. So that would mean if only one of the two were negative. Then you would be working with a hyperbola. So given a set of conic sections in general, you want to have a good solid foundation in identifying what type of conic section you would be working with. And after that, use the methods that you've learned in the previous lessons to identify all the different important parts of each conic and ultimately graph them. But identifying is what we're working with in this particular section. So here's an equation that fits the general form standards. And how do we determine what type of conic this is? Well, first thing I notice is there's only one squared variable. And when there's only one squared variable, you're dealing with a parabola. Next here, I have x squared over 16 equals 1 minus y squared. With a quick change, I can actually show pretty certainly that this is the equation of an ellipse. If you jump too quickly at that, you might end up saying that it was a hyperbola. But in general form, you have all of your terms on one side. And so those rules only work if both the a and the c term are on one side of the equation. All right, now this is more like in general form. If we look at the a term and the c term, they're equal to one another. So that is going to produce a circle. Lastly, I have in general form again. A is -3, C is 2. Since they are not the same sign, that's going to be a hyperbola. And that's as easy as these questions can be. Next, let's convert the following equation from general form to standard form. So 2x squared minus y squared plus 12x minus 4y equals 12. So in order to do this, you have to do some sort of form of completing the square. And in order to complete the square, we can only do it in one variable at a time, and we need to group those together. So 2x squared plus 12x grouped together plus negative y squared minus 4y equals 12. Now, if I factor out 2 from my x's, which I would have to do because in order to complete the square, you need to have the leading term coefficient on the squared term equal to +1. And I'm going to need to factor out a negative from the second set of parentheses. Now, completing the square, you just have to decide on a term to add into your quadratic in order to make it a perfect square trinomial. So you've learned many times over that if you take the b term, which in the x's, that's going to be the 6, you divide it by 2, that gives you 3, and then you square it. So that's going to be 9. Now, you can't just arbitrarily add 9 to one part of the equation and nowhere else. So in order to keep things balanced, what we're going to do is add 18 to the other side of the equation. And I know you're asking, why 18? You were talking about 9. Well, the thing is, everything in this set of parentheses is multiplied by 2, including the 9. So I didn't actually add just 9. I added 18. So I have to do the same to the other side of the equation to keep it balanced. In the y's, my b term is 4. If I divide that by 2, that's 2. When I square that, that gives me 4. But if I'm adding 4 to this side of the equation, I am effectively subtracting 4 because that negative affects everything in those parentheses. So I need to subtract 4 on the other side. So now that gives me 2 times the quantity x plus 3 quantity squared minus y plus 2 quantity squared equals, all right, so 12 plus 18 is 30, minus 4 is 26. And then to finish this off, this looks like the equation of a hyperbola to me because of the minus. So the standard form always has these equal to 1. So I'm going to divide everything through by 26 to make that happen. 2 goes into 26 13 times. So in standard form, I have x plus 3 quantity squared over 13 minus y plus 2 quantity squared over 26 equals 1. Now, if you're wondering where I got the x plus 3 quantity squared, if you factor out x squared plus 6x plus 9, you're looking for two things that multiply together to give you x squared. So x and x. Two things that multiply together that give you 9, that's 3 and 3. This is called a perfect square trinomial because when you factor it out, the factorization is a perfect square. It always ends up being whatever your b term is this is half of your b term. That's a property of your perfect square trinomials. Convert the following equation from general form to standard form. Let's see what happens here. So again, I'm going to group the x's and the y's together. So 32x plus 6y squared minus 36y equals negative 70. Now I'm going to factor out 4 from the x's. That leaves me with x squared plus 8x. Then I'll factor out 6 from the y's, so that's 6 times y squared minus 6y. Now, if I take 8, divide it by 2, that's 4, and square it, I get 16. But I'm not just adding 16, I'm adding 16 times 4, which is 64. So I need to add 64 on the other side. Next, I have the negative 6. If I divide that by 2, that's negative 3. When I square that, that's going to be 9. All right, but I'm not just adding 9, I'm adding 6 times 9, which is 54. So I'll put 54 on the other side. So I now have 4 times x plus half of my b, quantity squared, plus 6 times the quantity y minus half of my b, quantity squared. Negative 70 plus 64 plus 54. Throw that into your calculator. You should get 48. Now I'm noticing this as a standard form of an ellipse. And if I divide everything through by 48, because in an ellipse, just like a hyperbola, that the other side, the right-hand side of the equation, is always equal to 1. So I'm just setting that up. 4 goes into 48 12 times. 6 goes into 48 8 times. 48 and 48 cancel. So I get x plus 4 quantity squared over 12 plus y minus 3 quantity squared over 8 equals 1.